So how do we do science? How do we study living things? There are different approaches. The first approach is make observations. We do that naturally as little kids when we go out and we watch robins pull worms out of the ground, when we try to sort out how a tree can grow sideways on a sand dune. We observe things. Collecting and analyzing our observations can lead to important conclusions. This kind of studying is going from very specific examples to more general, drawing general conclusions from specific information. That kind of reasoning is actually called inductive reasoning. And a great example of someone who used inductive reasoning to do fabulous science is Jane Goodall. Jane Goodall studied chimpanzees. Back in the 1960s, she approached a scientist and said, "Can I please study chimpanzees?" And she went to Tanzania, to a national park there, and she started observing them. Not very many people knew much about chimpanzee behavior and their social lives. In fact, few people, no one had documented it. And she went out and made careful observations. She watched everything. She recorded everything. And later, she then used those observations to draw some general conclusions about chimpanzees, like they're using tools. They're tool makers and users. They have really complex social lives, and social lives that she could that were predictable, that she could describe. These are the kinds of things that nobody knew back in the 1960s. You've probably done a good deal of discovery science in your own life. But what we tend to do after we do discovery science is we start to do hypothesis testing. And that's the second type of doing the way that we do science. We form and test hypotheses. So you've already done some research. Maybe you have some ideas in mind. Maybe you've made some observations. At this point, you might propose a hypothesis that attempts to explain an observation and then can be used to make specific predictions. So if chimpanzees are tool users, then maybe and they learn their tool use from their parent, their mom, then maybe we will see different types of tool use in different troops of chimpanzees. In this case, we're reasoning from general to specific. We start with a general explanation, and if it's true, then we can make specific predictions. This is deductive reasoning. So you've proposed your hypothesis. Next, you design and run an experiment that tests your hypothesis. When you're testing your hypothesis, you're going to need to pay attention to controls for your experiment. You're going to think about what are the independent variables and the dependent variables in your experiment. Your design is going to have to be pretty tight, pretty carefully designed in order to actually test your hypothesis. Go ahead and read about the details of experimental design in your textbook. Once you've run your experiment, you'll then need to draw conclusions about your results, right? And really about your hypothesis. Do these data fit well with my hypothesis, or don't they fit well with my hypothesis? We can use data to reject a hypothesis. Say, wow, under the conditions of this experiment, these data kind of tell us that our hypothesis doesn't make sense. We're going to have to reject our hypothesis. But we can't prove our hypothesis to be true. Instead, we say something like, these data fit really well with my hypothesis. they support my hypothesis. They don't prove that it's true. I mean, there might be some other reason for my data to be this way, but at least they fit well with my hypothesis. So the data can support my hypothesis. It's easy to make the mistake of saying, oh, the data show my hypothesis to be true, or prove that my hypothesis is true. But sometimes our data, we don't really know if our data are proving our hypothesis or if they're just, maybe there's some other explanation out there that we haven't even thought about. So we need to step back and say, wow, it looks like our data fit pretty well with our hypothesis. They support it. Once we've got some data and we've interpreted the data, we then need to tell other people about the results of my experiment and its conclusions. So we might write a paper or go to a conference or give a poster at a poster session. And then you're going to talk to other people. And by talking with other people, by looking at the results together, you're probably going to want to do more science. We might generate new hypotheses to test, or a different experimental design to test the same hypothesis. That's the exciting part of science, right? We tend to think of science as being very linear, and with this kind of reasoning. Here's what we do. We propose our hypothesis, we run our experiments, we draw some conclusions, we report the results. But science is probably more like this. It's kind of circular. So yes, a big part of doing science is first just exploration and discovery, observing the natural world and sorting out what's going on a little bit and coming up with some ideas. Sometimes the community helps us. Maybe it's a community of scientists, or the more general community comes up with ideas or questions or something that they want answered. And after we do some of our testing, we might then find out that this is useful information for our community, for the society as a whole. And the society might say, yeah, but we want more. We want to understand it more fully. And we can think of something like COVID as being a perfect example of this, where there's this back and forth about how COVID-19 works. What are the what is it doing to our body? We're trying to sort that out, and we're trying to come up with medicines that help to mitigate the effects of COVID-19, and in fact a vaccine that's going to prevent people from getting COVID-19. But science is all about kind of a combination of non-linear information and using it back and forth with a lot of community and a lot of communication between the scientist and the people around her or him. All right, we will look at an example of doing science next.